save it. So the basics about electric current, I'm going to quickly go over this topic once again for you to understand it. The formula for electric current, how you define electric current, right? So electric current is the flow of electric charges. I explained to you earlier that what electric charges are, right? It could be the electrons, right? Any charged particle that flows from, it could be a negatively charged particle, it could be a positively charged particle, it could be a proton as well, right? So when charges flow, they basically produce electric current, right? It is the flow of charge. This is the reason why this formula Q over T is used to define electric current, where Q is charge and T is time. Charge per unit time, right? For example, if this is a wire and this is point one of the wire and this is the second point, and a charge sort of flows through this wire from point one to point two in a specific given time. So the time is basically time period. Now, the time the electrons take to flow from the first terminal to the second terminal is basically electric current. It's Q over T, charge per unit time. You specify a set amount of time and then you see the charge that flows in that particular time. The current unit is amperes A, right? And 1 ampere is equal to 1 coulomb over a second, because charge is measured in coulombs, right? C and time in seconds. So C over S equals A. Coulombs over seconds equals ampere. This is how you can represent this formula in form of its units as well. I'm sure you already know this theory of what do you say, the prefixes, right? If let's say the amount of current is very small or very large for that matter, you can always represent them in form of their exponents, right? For example, if it's 0.001, so it could be represented as 1 milliampere, or 1 times 10 raised to the power of -3 amperes, right? So this is just the use of prefixes to represent the smaller values of currents. Similarly, 10 raised to the power of -6 amperes could be written as 1 microampere, okay? So yeah, you can always represent any, I mean, it's not just specific to current, any physical quantity for that matter can be written in form of the prefixes. So ammeter is used to measure the size of an electric current, okay? This is a device, this is an instrument that you use to measure the size of electric current. It is connected in series. Now, this connection in series means that this is, look at this is an ammeter. So the circuit has to continue this way. You can have a bulb in the circuit, you can have a resistor in the circuit, you can have a battery or a cell in the circuit, right? So this is how, this is called a series circuit. We're gonna be discussing these parallel and series circuits in detail in the upcoming lectures. But for now, just know that ammeter is just connecting series. A series is, for example, if you break the circuit down from this point, and if you open up these wires, this is how the circuit would look like. Yeah, do you agree with me, Iman? This is how it would become, right? A wire,
Yeah.
a wire just having all of these components connected in series. This is why it's known as a series circuit. But when you connect it, yeah, you take one of the components on the other side, you just complete the entire circuit in a loop, okay? So yeah, this is a series circuit, and on an ammeter has two terminals, a red terminal and a black terminal, okay? So the red terminal is always connected to the positive side. This is the positive side. And the black terminal is always connected to the negative side of the battery. This A is the circuit symbol of an ammeter. All clear up till now?
Yeah.
Okay, so convectional current, once again, I'll quickly explain what convectional current is. So convectional current is whenever the electric current flows through a metallic conductor due to the flow of negative charges, it is substituted by an equal amount of positive charges flowing in the opposite direction. So if you look at this diagram, The electrons, they basically flow from in this direction, in the arrow's direction, from left to right. Now we're talking about a metallic conductor. Why? Because it has free electrons. And now an equal amount of positive charge will substitute this negative charge. So there's going to be a positive charge flowing in the opposite direction from right to left. So if your negative charge moves from left to right, the positive charge would move from right to left to substitute this change taking place. Now this negative charge is just known as um the flowing positive charge, okay? Sorry, electron flow. And this positive charge is known as the convectional current. So this conventional current is basically is a theory that a concept that we understand to sort of comprehend how the positive charges flow in a direction, an amount opposite to the electron flow, okay? So, for example, look at this. We withdraw 50 electrons from object A. Now it carries positive 50 charge. Now add 50 protons to object B. The object B now also carries 50 charge. This example shows that withdrawing electrons is the same as adding protons. Yeah, so this is the reason why if the electrons move in one of the directions, the protons would move in the opposite one. So withdrawal of electrons is equal to addition of protons. And withdrawal of protons is equal to withdrawal of is equal to addition of electrons. Yeah, so for example, if you take out 50 electrons, so you'll be left with 50 more protons, yeah, plus 50 charge. That's equivalent to adding just 50 protons and not just doing anything with the electrons, yeah? So withdrawal of electrons, a certain amount of electrons, is equal to addition of that same amount of protons to a complete system. This is the concept of electron flow and conventional current, all right? Is this clear?
Yes.
Okay. Now let's look at electric circuits. Now look at this table. This is very important to understand the devices, the symbols, and the representations in a circuit. So look at the switch, the cell. I'm gonna just circle the ones that we're gonna be using very commonly. A cell, a battery, the lamps. Look at the AC power supply as well, okay? We will be using ammeters, voltmeters, fixed resistors, variable resistors, fuses. Look at the capacitor as well, coil of wire, then a transformer, a bell, a thermistor, an LDR, light dependent resistor, semiconductor diode, and an LED, light emitting diode. So you see, these are all the symbols of the components and the devices that we'll be using in our circuits. You can refer back to this table whenever you need to, all right, because it is very important for you to understand these representations. So there are four main components of an electric circuit. The first one is a source or battery or a cell. The second one's a bulb, which could be a load. There's a conducting wire, and then there's a switch. See, source could be, this is how a battery is represented, multiple cells, and this is a single cell, okay? The bigger one is positive side and the smaller one is negative, positive, negative, positive, negative. And then there's a wire that's connected to positive side, and then there's a wire that's connected to negative side. The first one's done. Now you need a bulb, a load, right? Because obviously you're sort of setting up this entire setup, having a battery, having these wires to carry the charge. Now there has to be a load as well, right? The load could be anything that you're basically supplying this charge to. So we could simply just connect a bulb here. Now this is how a bulb is represented, right? Lamps or bulbs. Then you see, these are the conducting wires, okay? This is the load. This is a battery or EMF, electromotive force, the EMF supply. And then you have a switch like this. These are four major components. Now you need all of these four components to complete a circuit, right? Without any of these, a circuit isn't complete. Then you can add other components as well. Yeah, okay. Just hold on for a second. All right. So you see, I was telling you that a circuit cannot be completed without these four components. The rest of all of these that are given in the table are just the additions. You can always add more devices, but you need these four minimum to complete a circuit. For example, you can add a resistor over here. You can add an LDR, um, or a diode for that matter, a semiconductor diode like this. You can add a thermistor here. Yeah, an LDR. Yeah, so there's an option to add as many things as you want to, but um, you cannot. You need these four to complete a circuit. Okay. Now there are three types of electric circuits: a closed circuit, an open circuit, and a short circuit. Just remember these three: closed, open, and short. I'm sure you must have heard about short circuits. Have you?
It's like when there's a spark.
When there's a spark, yeah. That's a consequence of a short circuit. When a circuit is very short and the current just takes the fastest or the shortest path, yeah, that is a short circuit. We're going to go into details later. And open and closed circuits are very simple as well. An open circuit is the one that's not connected, having an opening, having a gap, maybe. Yeah, a broken circuit for that matter. And a closed circuit is a complete circuit. If I remove, let's just switch from here, now that's going to be an open circuit, no connection. And when the switch closes, right, when the you see, a closed circuit means an open switch. Yeah, whenever, let's say, you're asked to, for example, turn on the lights, you turn on the switch, and then turning a switch on is essentially closing a circuit for the current to have a complete channel to get passed through. And let's say whenever you ask to maybe switch off the lights, so switching a component off is essentially opening the circuit or breaking that current channel. All right, look at these three diagrams here. A circuit is said to be open circuit if there is a break in the path. This is an open circuit. The switch is open. You see, if a switch is like this is an open switch. And a switch like this is a closed switch. All right. So look at figure 19.3. This figure basically represents an open circuit where the switch is also open. And the circuit cannot be completed. There's a break. Then look at the first one, the closed circuit here. This is a closed circuit. The switch is closed and current has a complete channel to pass through. And the last one is a short circuit. Why? Because look at the current channel. Now this was the load, yeah? This was your load, but the current is just not going to that load. What's happening here is that the current is moving, is sort of bypassing your load. Now what's happening is the same amount of current that was sort of provided over here, approximately same. We're assuming that there's least resistance in the wires. It's sort of bypassing this bulb and it's traveling back to the negative terminal. This is the reason why a short circuit occurs, because the current is not just getting consumed. Okay. So the current will always take the easiest path. You see, for example, let's say if this is a circuit, okay, and you've got these two paths. Now look at this. The current travels from this side. Now there are these two paths for the current to complete its journey. There's a red path and there's a black path. Iman, what do you think? Which path will the current take? This is path number 1 and this is path number 2.
The red one.
The red one. And why is that so?
Because it goes to all the circuit.
Not essentially, but the reason for that is because it has no resistance. It is the shortest, easiest path. You see, even if let's say the circuit was like this, and the bulb on this side, the current would go from here. It won't just go to the entire circuit. Why? Because the current would in any case try to avoid the load, right? The current will avoid the load. Why? Because the load is sort of resistance. This load provides resistance and the current does not like resistance. It's going to get reduced. So it'll try to avoid that resistance in any case. And this is the reason why it'll take the shortest path, the easiest path. And that easiest path would lead to a short circuit. Got it?
Okay.
Yeah. Let me know if there's any questions so far.
No question.